Suppose that I have a piece of rod, just a piece of rod, and I move this rod up and down so that one end of the rod keep pushing in and out of the water. This would generate a ripple. It would generate a ripple continually that keeps spreading outwards. I'll try to draw that. So this ripple will spread out. Okay. Now suppose now that I have another rod. Not so far away, maybe just a few wavelengths away, a similar rod, and I also move that up and down. So maybe my right hand holds onto this and left hand to this, and I'm going to push both of them up and down at the same time and at the same frequency. Okay, so this other rod will do the same. It would start producing ripples, and ripples that will start traveling outwards. Now, but what we will see is that the two sets of ripples will start crossing into each other. They will start interfering with each other. Now, what happens when they interfere? Right, it's what we call an interference pattern. And we use the word interference to describe this situation where two waves meet each other and give a particular pattern. Now let's try and understand what's going on when the two waves meet each other. Now one way we can understand this is to think about, say, a particular point some distance away. Let's say that point. And I'm going to start by thinking about the separate waves that come to this point from each of these rods. So maybe let me put that point here. Okay, suppose that this point is at the same distance, right, from both rods. So what happens then is that I would have if I follow a line from one rod to this point, if I follow a line along the surface, I would see the surface going up and down, to here, and I would see this wave, and this would be a progressive wave, a traveling wave, meaning that the peak, if I follow a peak on this wave, I'll see the peak traveling outwards. And we expect that because these are ripples, and ripples travel outwards, and the peak is just a peak of one of the ripples that is spreading out. So let's have 1, 2, 3, 4, 5 peaks from the rod to this point. Likewise, I would expect if I follow a line from the other rod to this point, I would expect to see a similar wave, but coming from that rod. Okay, so let me try and draw that. 1, 2, 3, 4, 5. So when these two trains of wave cross each other at this point, the peak would meet the peak, right? The peak of the wave from there would meet the peak of the wave from there. Now, if the two peaks meet, as we've seen in the topic on superposition for waves traveling along a rope, when two waves meet, the displacement would add together. So if I have two peaks meeting, peaks will be upward displacement, right? The peak would mean that the water there is displaced upwards. So when the two peaks meet, I will get an even bigger displacement. Okay, so that's what would happen in this case. But the peak is not there all the time. We must not forget that this is a traveling wave. So the peak would continue to travel outwards. So which means that after a short time, it will be the trough, right? The bottom here. Call it the trough, T-R-O-U-G-H, that would arrive at this point, and likewise the trough from the other wave would arrive at this point. So when the trough meets the trough, I have two downwards displacement meeting each other here. So that would give an even bigger downward displacement. And you can imagine that after a short time, the next peak would have arrived here, right? That one and that one would have arrived at this point, and then that will give a big upward displacement again. So the effect of these two waves meeting at this point would be a displacement which will be this point going up and down at twice the displacement of the separate peaks. So that's what we would expect. And we describe this by saying that the two waves act constructively, right? By giving an oscillation here of a bigger amplitude than the separate waves would. Okay, so we kind of understand what happens at this point, and this is a situation where the point is at the same distance from both rods. So we have the same number of wavelengths from both rods. So therefore, the peak from one rod will always meet the peak from the other rod. Likewise, the trough from one rod always meet the trough from the other rod, because it's symmetrical. It's the same distance. Now let me think of another point, all right, which is not at the same distance from the two rods. Let me think of a point maybe a bit further away to this side. So this point would be a bit closer right here. This point will be closer to this rod than it is to that rod. Okay. Now, so therefore, it is quite possible that we would again have one wave coming from each. If we follow a line from here to here, we would expect to see again like before, a traveling wave going past this point, right? So a traveling wave, and likewise I'll see a traveling wave from there. But this time the peak does not have to meet the peak anymore. It is possible, for example, that it is the trough of one wave that meets the peak of the other wave. So whereas the peak from that wave wants to give a displacement upwards, the trough from that other wave would have a displacement downwards. Now if that is the case, then the two displacements will cancel, and there will be zero amplitude here, zero displacement here. And what happens after a short time is that the peak from that wave would come over to this point, and the trough from this wave would reach this point. And once again they have opposite displacement, and the resulting displacement would be zero. So because of this, we would find that the displacement such a point would always be 0. And this happens when a peak meets the trough here. Now, what kind of distance can give this situation? Well, it is when, for example, let me just count the number of waves here. Let's say if I count this one, 1, 2, 3, 4, 5. So for that wave, I have 5 wavelengths, right? How about that one? 1, 2, 3. That's a peak and that's a trough, right? So 1, 2, 3, 4. But that's in the middle, so it's 3.5. So from there to there, the distance is 3.5 lambda. So we have a half there, right? We have a half there. So the difference between these two is 1.5. Right? 5 minus 3.5 is 1.5. So you can see that the half there, it is the half there that gives us this situation where a peak can meet a trough. So this would happen if the difference between the two halves has a half wavelength, meaning that it can be half or 1.5 wavelengths or 2.5 wavelengths. So that's the kind of situation. So in this case, we would expect that there will be no displacement here, which means that actually the water surface here will be at rest. All right, you may have lots of ripples happening all around it, but that particular point would not move because of this reason. Now let me think about the idea, very briefly mention the idea of coherence. Now these two rods, as I have mentioned, is going up and down together, meaning that when this goes down, this also goes down. When that goes up, this also goes up. So they are going up and down, they're synchronized, they are doing it together. And if they're doing it together, I will always have, say at this point, I would always expect that the displacement would be opposite, as I described just now, and that there will be the resulting displacement here will be 0. And at the point, like at the earlier point where it is same distance from those two rods, I would expect that the peak would always meet the peak, or the trough meets the trough, and there would always be a maximum oscillation at that point. So this kind of this pattern, all right, where I have a big oscillation at some point and no oscillation at some other points, right? It can also happen at other places as well. If I have, in order to have a fixed pattern, that means that this point would always have no oscillation, for example, the two rods must always go up and down. The two motion of the rods must always be together, right? The way that the waves are generated. Now we describe this using the word coherent. Coherent, all right. I will talk a bit more about the definition of coherent later on, but for now, let's just appreciate that coherent means that the two sources of the wave, right, the two things that produce the wave, the motion has to be related in a certain way, right? There has to be a fixed relation between them. For example, they have to move up and down together, or maybe when one move up, the other must always move down. Okay, then the pattern will be different, but it would also be coherent.